In this video, what I like to do is introduce you to a couple different design methods that exist and kind of talk about the idea of factors of safety. We haven't done that a whole lot yet, and this is really the part of the semester where we need to introduce that. Thus far, we've been doing allowable stress design, and we've been doing that with timber. And basically with allowable stress design, it's the idea of taking our actual stress calculation and comparing it to some allowable stress value. In this case, the diagram shows what it would be for bending stress, or sorry, the equation there for bending stress. But essentially what we're doing is we're taking the loads that we expect to work on the structure, calculate the actual bending stress that we would expect, and make sure that we're less than some sort of an allowable value. And there's actually a number of different ways that we can compare loads. And if we're doing design for real, we'd have to pay attention to all these different load combinations. You can see that there's dead loads, DLs, there's live loads, there's special roof loads, wind loads, and earthquake loads. And they factor in some different sorts of factor of safeties in all of these combinations. The idea here is we'd have, let's look at this particular line right here. This one would assume that we've got the full dead load and only 3/4 of the maximum live load and 3/4 of the anticipated roof load. And the more loads that we consider, the less likelihood that we would experience the maximum loads all at the same time. For instance, an earthquake happening on a structure right when you've got the snow load is the greatest it's ever been, and you're having a giant party inside the house, and all the people inside the house are creating the biggest live load that there's ever been. And the likelihood of all of those events taking place at the same time is pretty slim, and so they have these reduction factors on there. ASD is a design procedure. It's great for introducing design, but it's really not the design process that is used as much anymore. Steel and concrete especially have moved over to a different design process called Lrfd. Timber is shifting more and more that way all the time. And what I'd like to do today is introduce you to as we transition into steel, introduce you to the Lrfd method of design. Lrfd stands for load resistance. Whoops. Can't write off the black there. Load resistance factor design. You'll see this in the textbook if you look there as well. But it's pretty straightforward as far as a conceptual idea goes. For any of the failure mechanisms that we would anticipate, this is the resistance part of the equation. We've got some sort of a failure limit where failure will occur. And then we have our anticipated loads. But we've got different kinds of loads, and rather than treat them all the same, we recognize that there's maybe different types of factors of safety that apply to the different loads as well as the different failure mechanisms. And so we treat them all individually. And with load resistance factor design, what we do is we apply a factor to the failure or the resistance mechanism and bring it down. And so we've created a factor of safety there. And then with our anticipated loads, we actually bring them up and create a factor of safety there. And so long as the failure or the resistance value is larger than the anticipated load value, then the design is correct, and we shouldn't experience a failure. So that's the idea here. Failure comes down with a factor, loads go up with a factor. Make sure that the loads still remain less than the failure. That's really all Lrfd is. It looks a little scarier when we look at the equation. I'll show you that in just one second. But the idea here, as I indicated earlier, is there's these different failure mechanisms such as moment and shear and buckling that we're going to expect to have to look at. And they'll all behave a little bit differently, so we have different factors to apply to them. And then the different types of loads that act on it, we also have to treat them a little bit differently as well. Okay, here's the Lrfd equation. Don't get scared by it. The left side of the equation is the failure side. The right side of the equation is the load side. So you'll notice that we want the failure side to be larger than the load side with the greater than or equal sign. The factor side, because we're bringing the resistance or the failure mechanism down, the factor over there should be less than 1. So 90% or 80%, and actually bring this side down. On the right side, the summation sign is simply just a fancy way of saying add all the loads together. Then we also have load factors over here, but we want them to be greater than 1 so that this side will actually go up. And then we simply consider all the different loads that may be acting on the structure. So you look at it mathematically, it's a little scary, but when you break it down and you actually talk about what's there, it's the same concept I've drawn on the previous page. Got 2 more slides we want to talk about here. The first one is the idea of what the loads actually are. And so again, we're bringing the loads up, and so the net effect is greater than 1. You'll notice that there's a few loads in there that are less than 1, but again, that goes back to that idea of all of the extreme events happening at the same time. All the extreme loads are on it at the same time. It's not very likely, but the net effect would still be greater than 1. These are the 2 load combinations that we will consider for the sake of this class right here. 1.4 times the dead load as one load combination, or 1.2 dead load plus 1.6 live load as a second load combination. You'll note that in the real world when they do design, there's several more load combinations they will consider, but for the sake of our class, we will consider just these 2 load combinations. And you'll see that in the examples as we move forward. All right, so this is where we this is where we raise the loads, make the net effect greater than 1. And then on the resistance side or the strength side, the failure side, any of those terms work, we want to actually bring the load down. And so if we're dealing with bending or flexure, then we reduce it by 90%, the allowable value. If we're dealing with shear, then we also reduce that by 95%. And you can see the other factors that apply there. We'll predominantly stay with bending and shear for the sake of what we're doing here. But again, there's some values as you run into these in the examples, you'll see these values as they get applied. Now, one thing that I do want you to note on this particular slide, these strength factors are specific for steel. If we are dealing with concrete, later in the semester as we finish up with concrete, you'll actually see that they use different values for bending and shear when we use the Lrfd method for concrete.